Hi students, today we discuss the electric displacement and also the Gauss's law in the presence of dielectrics. Okay, we found that due to the polarization, bound charges accumulates in the dielectric material, that is volume bound charge minus del dot P within the dielectric, and also surface charge density sigma p v dot in on the surface of the dielectric. If we put our dielectric material this is some free charges, and this free charge is denoted by rho f. This rho f generates an electric field, that you are well aware of this electric field. Within this external electric field, our dielectric material gets polarized, and because of this polarization we have a volume charge density rho b, and the electric field at this point, I need to find out the electric field. Here this field, this rho f is the free charge. This free charge produces some external electric field. Let us say this is the external polarizing electric field. External polarizing electric field. Within this external electric field, this dielectric material is getting polarized. This polarization gives rise to a bound charge density rho b. Now the electric field at this point E that I need to find out. This electric field is not because of this, not only due to this bound charge, but also due to the free charge. Both this bound charge and also this free charge produce an electric field at this point. Okay, this rho b is the bound charge due to the polarization. Due to polarization. Okay, now we are familiar with this equation, that is if we have a charged body, it contains a large number of free charges rho f, then at a particular distance the electric field at this point can be easily written like this: 1 by 4 pi epsilon 0 volume integral rho d tau divided by r square. Okay, d tau is the small volume element. But here we have only the free charges, but the situation here is not like this one. Here we have both the free charges and also the bound charges that arise from the polarization. The Gauss's law in this equation can be written as del dot E is equal to rho by epsilon 0, where rho is this free charges only. But here the case is not like that, slightly different. Different in the sense, here this Gauss's law needs to be modified. Thus I can write this Gauss's law here in this case. This del dot E can be written as rho by epsilon 0, where this rho, here the source of this electric field is this free charges, but here the source of this electric field is both the free charge and also the bound charge. Therefore the rho here I can written as rho f plus rho b. Okay. Therefore this equation can be written as rho f plus rho b divided by epsilon 0. Okay. We are familiar with this equation, that is volume bound charge density due to the polarization can be written as minus del dot b. I am going to replace this equation here. Therefore del dot E can be written as rho f minus del dot P divided by x0 0. Okay. Or if I take this epsilon 0 to left side, this can be written as del dot epsilon 0 E is equal to rho f minus del dot P. Okay. I combine these two divergence terms, that is del dot epsilon 0 E plus P is equal to rho f. This quantity can be written as D, that is electric displacement vector, because this is a vector quantity. That is, D can be written as epsilon 0 E plus P. Therefore, the divergence equation can be written as del dot D is equal to rho f. This is the electric displacement. Okay, this is Gauss's law in the presence of dielectric. This is Gauss's law in the case of the dielectric. Here, everything is the same. In the case of free charges, this was a Gauss's law, del dot E is equal to rho f by epsilon 0. But in the case of dielectric, that is modified, and del dot D is equal to rho f. Here, I would like to mention a few more things here. The free charges that we have mentioned here, there can be any charge given to this dielectric material. That we can supply any amount of free charge to this dielectric material. Because of this free charges, the material get polarized, and the volume bound, the polarization will give rise to the volume bound charge density. And then the field at a particular distance from this polarized object can be due to the both of these charges, volume bound charges and also the free charges. Okay. If this is a differential form of the Gauss's law for dielectrics, then let us see what is a integral form of this Gauss's law. Okay, this is the integral form of the, here we will see what is the integral form of the Gauss's law. We have the differential form, that is del dot D is equal to rho f. Now take the volume integral. That is nothing but V del dot D dot is equal to, right hand side also take the volume integral. Here, now apply the Gauss's divergence theorem. Gauss's divergence theorem converts the volume integral to the surface integral. The left hand side of this equation can be written as del dot D dot is equal to surface integral d dot dA. Therefore, the left hand side of this equation I can written as surface integral d dot dA. The right hand side of this equation, what I will replace, let us see. We know the volume charge density rho can be written as dq by d tau, or dq can be written as rho d tau. This, if I integrate this dq over volume, this will be rho d tau. This is nothing but the total free charge, total charge. Here this is a total free charge contained in the volume of the dielectric material. Therefore, this equation can be written as, instead of volume integral rho f d tau, I can write this is a qf. If I then this equation, if I put this as equation number 1, then equation number 1 can be written as surface integral d dot dA is equal to QF. This is a integral form of the where QF, this QF is a total free charge enclosed in the volume. Okay, now let us move to the case here. If this is a divergence of del dot D, let us see what will be the curl of del dot D. What will be the result of del dot D? Del cross D, what is the result? We know that del dot D is equal to rho f. If this is a free charges, rho f, and the field produced by these free charges produces a polarization in the dielectric material. As a result, the electric field at this point that will be responsible for both this volume bound charge density and also the free charge density rho f. Here the electric field is still static because all the charges are not moving. So del cross E will be 0 because this electric field at this point is static electric field. Now the question is del cross D, what is the result? Now we know that D electric displacement vector can be written as epsilon 0 E plus polarization P. Then if I take the divergence, so curl, this will be del cross epsilon 0 E plus P. This is nothing but epsilon 0 del cross E plus del cross P. The result here, del cross is 0. Therefore, del cross D can be written as it is nothing but del cross P. Now we will do a small problem based on this to find out the electric displacement. This is a problem number 4.4, solved problem in the Griffith textbook. There is a long wire carrying a uniform line charge lambda is surrounded by a rubber insulation out to a radius A. This is shown in the figure. This is a long wire that has a charge density lambda and radius A. Find the electric displacement. To solve this problem, let me draw a Gaussian surface. This is a cylindrical Gaussian surface of radius r and length L. Now we have the equation that is an integral form of the Gauss's law in the case of dielectric, that is Q free charge enclosed. Here we can write dA because the area vector and displacement vector both have the same direction. Then the total charge enclosed. If lambda is a linear charge density, then total charge enclosed divided by total length, then Q enclosed can be written as lambda L. If you substitute here, this will be lambda L. The surface area of this cylindrical Gaussian surface, that can be 2 pi r into total length. Then this lambda length and length will cancel. Then electric displacement vector D can be written as lambda divided by 2 pi r. Then direction is along the radius vector r. Okay. This equation holds good within the insulation and also outside it. Now, the electric displacement due to this object, that means we have to find out the electric displacement inside as well as outside, but this is valid in both cases. electric displacement. If it for outside, this R will extend to here, and therefore this equation is valid in both inside and also the outside. But here the outside, the polarization P is equal to 0, because there is no charges outside this body. Therefore, the polarization P is equal to 0. Therefore, electric displacement vector can be written as A epsilon 0 E plus P. This is equals to 0. Therefore, this is epsilon 0 E. Here, the electric field outside, E out, can be written as D divided by epsilon 0. D we have inside and outside, both of the same relation, that is lambda divided by 2 pi r, and here we have epsilon 0. That is E outside can be written as lambda divided by 2 pi epsilon 0 r. Then inside the rubber, the electric field cannot be determined since we don't know the polarization. Another example is we need to find out the electric displacement due to a uniformly polarized sphere. Okay, it is given that the sphere is polarized along this z direction. That is, you know, the polarization is from negative to positive. Then the polarization P is given as P0 z cap, and you know the electric field inside this dielectric material because of this polarization, that is, charges accumulated will be along this direction, that is from positive to negative. This is the direction of the electric field. Okay. The surface charge density because of the polarization, that is P cos theta. Everything we have already discussed. The electric field inside can be written as, we have derived this relation, that is minus P0 divided by 3 epsilon 0 z cap. Okay. Now I am interested to find out the electric displacement inside this polarized material, this polarized sphere, that is D inside, can be written as the expression epsilon 0 E plus P. Here instead of E, I can substitute this minus P0 by 3 epsilon 0. It is epsilon 0 into minus P0 by 3 epsilon 0 z cap plus P replaced by this expression P0 z cap. This epsilon 0 get cancelled. Then the remaining thing is z cap. If I take P0 z cap, if I take it outside, this will be 1 minus 1 by 3. That is P0 z cap into 3 minus 1 by 3 means that is 2 by 3. That is, inside the dielectric material, the electric displacement vector of this uniformly polarized object is nothing but 2 by 3 P0 z cap or 2 by 3 P. Next topic is our boundary conditions for the electric displacement vector T. We have already know that the electrostatic boundary conditions, that is the tangential component of electric field is continuous. Second one, the normal component of electric field is discontinuous across the boundary. That if there is a boundary charge, surface charge density is sigma, and our electric field is traveling from the this medium. Let us say this is a line below the boundary. Therefore, I can write this is E below, and the boundary conditions will help you to determine what will be the electric field in the second medium. That is, this second electric field in the second medium can be written as this is E above. Okay. While deriving the boundary conditions for the static electric field, we resolved the electric field components into two. That is, one is the tangential component, that is, let us say this is a parallel component, E parallel below and E perpendicular below, and also this is a E parallel above, and this one E perpendicular above. In this way, we resolved the components into E parallel and E perpendicular, that is tangential component and normal component in the below case, tangential component and normal component in the above case. Okay. The tangential component of the electric field E is continuous, means these tangential components are continuous while traveling this electric field vector from this medium to another medium. In the similar fashion, our electric displacement vector is traveling from the first medium to the second medium. Then what will be the boundary conditions for this electric displacement vector? Okay. Let me consider first this boundary condition. Normal component of the, what will be the normal component of the electric displacement vector? Here also we can resolve these two vectors, that is D below can be resolved into two, tangential component and a normal component. The tangential component can be written as D parallel below, D perpendicular below. This is this vector, that is this one. Similarly, we can resolve this upper vector, that is D above D parallel above, D perpendicular above. Now, if I write the boundary condition for the normal component of the electric field is discontinuous, that is E above, normal component means perpendicular component, minus E perpendicular below, electric field in the normal component in the medium 1, normal component in the medium 2. This is discontinuous by a charge density sigma by epsilon 0. This can be written as epsilon 0 E perpendicular above minus E perpendicular. If I take the multiply epsilon 0 throughout this equation, is E below is equal to sigma. This can be written as, if we have seen that D is equal to nothing but epsilon 0 E, then if I substitute here, this will be D perpendicular above minus D perpendicular below is equal to, this is nothing but sigma f, that is a free charge contained in the body. which means similar to the electric field, the normal component of the electric displacement is also discontinuous. Okay. Now let us see the second one, that is the first one, tangential component of the electric field is continuous. Then let us see what will be the tangential component of the electric displacement vector in the two media. This is very simple. The procedure is the same as that of the here actually I am not doing the derivations of these boundary conditions because I have already explained in detail when we discussed boundary conditions for the electric field. Therefore, let us see that tangential component of the electric field. Tangential component of the electric field boundary condition can be written as, that is, this E parallel above minus E parallel below equal to 0. If I multiply with epsilon 0, that is E parallel above minus epsilon 0 E parallel below is equal to 0. This is nothing but D, electric displacement vector D parallel above minus, this is nothing but D parallel below, that is equal to 0. Or this, the meaning of this expression is the parallel component of the electric displacement vector is continuous. Therefore, I can write D parallel above is equal to D parallel below. The tangential component is tangential component of electric displacement vector is continuous across the boundary, whereas the normal component of the D is discontinuous across the boundary. Okay, if that is the, this is the maybe the first boundary condition. Second boundary condition that we have already obtained, D perpendicular above minus D perpendicular below is equal to sigma f. If the medium does not have any, the boundary does not have any charge, if it is charge free boundary, then sigma f will be 0. Then in that case D perpendicular above will be equal to D perpendicular below, that is the normal component of the electric displacement will be continuous if the boundary does not have any charge. Okay, that is the normal component. In the usual case, if the boundary have a significant charge density sigma f, then the perpendicular component of the electric displacement vector is discontinuous across the boundary.